Welcome back, builders. I am so excited to welcome you to this explainer on behalf of Forge College. If you've been following our journey from EVM to SVM, you know we've been tackling some massive paradigm shifts. In our previous lesson, we looked at the core account model and uncovered a fundamental difference: how Solana separates logic from state. But that separation introduces a brand new, incredibly fascinating puzzle. So today, we're exploring deterministic addresses and ownership patterns. We're going to learn exactly how programs on Solana securely own and manage accounts without ever needing a private key.
All right, here's our agenda for today's engineering session. We're going to hit the private key dilemma, the PDA blueprint, the bump seed mechanism, some real-world Rust code, and then wrap it all up. Let's jump right in.
Section 1. The private key dilemma. Where exactly is the key? Okay, so to really appreciate this clever engineering blueprint, we first have to understand the core problem we're trying to solve here. And it leads us to this kind of funny, almost paradoxical question. Where is the private key? You see, normally to authorize an action on a blockchain, an external user signs a transaction with their wallet's private key, right? But a program is literally just code sitting on the blockchain. It doesn't have a secret hardware wallet hidden away or a seed phrase scribbled on a piece of paper. So how on earth do we authorize actions for an account if we essentially have to throw the private key into a digital black hole? Well, to answer that, let's briefly look back at our EVM roots. If you're coming from Ethereum, you're totally used to a world where smart contracts just store their own state directly inside themselves. The authorization is kind of implicit. But Solana's different. It requires explicit program-owned addresses because the programs themselves are stateless. All that state lives in separate accounts, and every single account has an explicit owner field. So we really need a way to create an account that is cryptographically guaranteed to be controlled exclusively by your specific program.
Section 2. The PDA blueprint. Let's get this blueprint revealed.
To solve this whole problem, we use our core invention, the Program Derived Address, or PDA. Let's actually draw out the components of this deterministic recipe. This is exactly how we forge a public key that explicitly has no private key counterpart. We start off with seeds, and these are just simple byte arrays that you choose. Next, we toss in the program ID, which is your program's public key, permanently tying the ownership of this new address directly to your code. Then we include a bump seed, just a tiny single byte adjustment. We take all these ingredients, mash them together, and run them through a hash function. And the result? Bam! Our PDA. A completely derived public key that the Solana runtime recognizes as being exclusively controlled by your program.
Now here is an absolutely crucial point. Because PDAs are publicly derivable, you must never use your seeds to store passwords or secrets. Seriously, don't do it. Seeds are just arbitrary short byte sequences. They can be human-readable strings like user profile or numeric identifiers, or even a user's public key, but they are completely public. You got to think of them as predictable namespaces or labels, not secret keys. Oh, and as a strict engineering constraint, each individual seed can be a maximum of 32 bytes.
All right, Section 3. The bump seed mechanism. Falling off the curve.
Now you might be wondering, what happens if our hash accidentally generates a normal, everyday wallet address? Well, this is where we introduce the absolute most fascinating gear in the whole machine, the bump seed. This brilliantly illustrates the core cryptographic trick of a PDA. See, regular Solana wallet addresses exist on what's called the ED 2055-19 cryptographic curve. If an address is on this curve, a private key exists for it somewhere. And we explicitly do not want that. We want an address that literally no human could ever possess the key for. So, the bump seed is an intentional single byte adjustment we append to our recipe to force the resulting address completely off the cryptographic map. We are intentionally looking for a parking spot that mathematically doesn't exist for normal user wallets. So, how do we find that exact off-curve spot? It's a deterministic search. Step 1, we combine our chosen seeds in our program ID. Step 2, the runtime appends a bump seed starting at the absolute maximum byte value, which is 255. Step 3, it hashes that whole combination and checks if the result is on the curve. Step 4, if it is on the curve, meaning a private key could exist, it just rejects it. It decrements the bump down to 254 and tries again. You can think of it like a giant mechanical dial clicking backward from 255 down to 0 over and over until the math just clicks perfectly into place, we successfully fall off the curve, and boom, we have our secure PDA.
Section 4. Real-world code. Let's look at the Rust implementation.
Now that we understand the schematic of seeds, program IDs, and that whole bump dial, let's actually look at how we apply this blueprint in the real world. In the Solana program crate, you've got this absolute powerhouse of a function called find program address. Here's the off-chain and on-chain workflow. First, you define your static and dynamic seeds, say a label like mySeed and a user's actual public key. Then, you pass those seeds and your program ID straight into find program address. This function does all the heavy lifting for you. It physically runs that mechanical dial search counting down from 255, and it returns two things, the valid PDA and the exact bump byte that made it valid.
But here is a massive architectural tip for you. Searching for that bump is computationally heavy. You really only want to search for it once, during account initialization. Once you finally find it, you store that single bump byte inside the account's data. Later on, when a user interacts with your program, you don't run that big search again. Instead, you use a different function, create program address. You feed it the seeds and that exact bump you saved earlier. Create program address acts as your strict quality control. It skips the search entirely, performs the math instantly, and will literally panic and fail the transaction if those inputs produce an invalid on-curve key. It's there to validate that the exact same bytes recreate the expected PDA.
So why go through all this trouble, right? One word, predictability. Because the derivation is entirely deterministic, your front-end client can instantly compute where a user's data lives without ever needing to look up some massive master registry file. If you want to find user metadata, your client just takes the string metadata and the user's wallet address, hashes them together, and knows exactly what account to query. It's brilliant. It allows for program-owned escrow accounts and just incredibly efficient decentralized architectures.
Section 5, wrapping up. Let's review our blueprint.
Let's take a step back and look at the final specifications of the PDA blueprint we just unveiled today. To summarize our engineering spec, PDAs have absolutely no private keys, making them inherently safe from external wallet takeovers. Literally, only the program can control them. Remember to treat your seeds as public namespace identifiers. Never ever store secrets in them. And always hold onto that bump seed inside your account state so you don't have to crank those cryptographic gears from 255 every single time a user interacts with your program.
Which leaves us with a totally fascinating puzzle for next time. If we can predictably map program-owned data and enforce ownership using these derivations, how do we use the same exact blueprint to securely hold and manage actual tokens? We are going to be answering exactly that in our next lesson on token holding patterns and associated accounts. Until then, I highly encourage you to visit forge.college to review the code snippets, practice recomputing these derivations, and just continue your Web3 journey. Thanks so much for joining me on behalf of Forge College, and I'll catch you in the next explainer.